Hi, and welcome to this third video in the series. And after looking at Newton's first law in the first video, his second law in the second video, what do you know, we're going to look at Newton's third law in this video. So what we're going to do is look at his third law and how that applies to problems involving connected particles. So off we go. Newton's third law. For every action there is an equal and opposite reaction, and there's two ways that this will come up with regard to questions on your mechanics section. First of all, let's just have a little think about the book sitting on the table. We saw this earlier, where we've got the downward force being exerted on the table, and we've got an upward force being exerted by the table on the book. And that's an example of our equal and opposite reaction, because obviously those forces are going in opposite directions, and the two forces are the same size. If we now consider our caravan being towed by the car, we've got the coupling here, and the car is exerting a force via the coupling on the caravan, and likewise the caravan is exerting a force via the coupling on the car. So we've got kind of tension and thrust both going on, equal and opposite forces. One is the car on the caravan, the other is the caravan on the car. And these two things are what we refer to as internal forces. And what we would need to do in order to be able to figure out what those forces are, we'd have to treat the two things as two separate objects. So I'd have to model the car as one particle and have to model the caravan as a separate particle, and then have a look at what's going on. We've also, with our car and caravan, got external forces. So, for example, the driving force that's been applied to the car that's causing the car to move forward would be an external force on the car. And what we've got, for example, would be a resistive force, for example, air resistance on the caravan in this particular case, that would also be coming externally. So if I wanted to know about these two forces, these external forces, then what I would do is treat the entire package as one single particle, and I'd look just at the external forces. I wouldn't worry about the internal forces because those would just kind of cancel each other out. However, if I just wanted the internal forces, I'd just, as I said before, be looking at just the car or just the caravan. So that's the idea. So let's have a look at an example where we're going to do just that. So we've got the car, mass 400 kilograms, towing a caravan. We've got a driving force, and we've got, exactly the same as we had on the previous slide, a resistance to motion. And we've got resistance to motion on the caravan, 150 newtons, and a separate one on the car. First of all, it says find acceleration of the car and the caravan. So car and caravan all in together. I'm going to treat them just as a single particle. So there we go. So I'm looking at that thinking, okay, what is my total mass? Well, it's going to be the 400 and the 750, so that's 1150. What forces have I got going on? I've got the driving force, the engine going that way. I've got the resistance motion, two separate forces, one on the caravan and one on the car, but because I'm treating this as one single particle, I'm going to apply them, it's happening both on this kind of this massive 1150 kilograms. And then, as I'm just chucking in the vertical forces just for completeness. So now if I want to find the acceleration, let's go for force equals mass times acceleration. Force is on the left, so I've got that force going in the positive direction, these two forces going in the negative direction, and then on the other side there's our mass times acceleration. A is the only variable I've got to worry about in here, so that's not a problem. We can do the solving nice and simple. So the acceleration 0.7 meters per second squared. Right, on we go. Tension in the tow bar. Now to do this, what I've got to do is have a look at either just the car or just the caravan, and it really genuinely doesn't make a difference. I've decided to go for the caravan here, so let's just now consider just the forces that are acting on the caravan. So what I've got is the tension in the tow bar, and then I've got the resistance to motion that's acting on the caravan. All the other forces, that's the driving force and the other resistance to motion, are acting on the car, so I don't need to consider them. You'll notice as well in this diagram I've got tension going on, just acting on the caravan, whereas tension is not appearing anywhere in here because I'm treating it as a single mass. So what we've got now is a different diagram. I've redrawn it because it's mechanics. First thing you ever do is draw a diagram. And there you go, there's my vertical forces, and off we go again. Tension minus 295 equals mass, and we know the acceleration of the caravan is 0.7, so we can plug that in. And so we've got the tension in the tow bar is 820. And what you might want to do now is just kind of pause the video and have a go at doing exactly the same calculation with the car and get to exactly the same figure. Okay, so hopefully that's kind of clarified the difference between the internal forces, how you deal with them, and external forces and how you deal with them. Right, on we go. So here we go, we've got our crane again that we saw earlier. So we've now got a crane and it's got two blocks P and Q sitting in a cage. So we've got a whole bunch of information, and first thing we want to do is find the tension in the cable. So again, because tension is a force that's external to the whole thing, I'm going to consider the whole system. So there's my cage, and it's got a total mass of 1,700 because my cage has got mass of 700. Sorry, try again. Cage got mass of 100, two blocks 700, 900. So there's my 1,700 kilos. Other external forces, we've got tension going upwards, and we've got weight going downwards, which is our mass times gravity. And it's accelerating downwards because it says the crane is lowering the two blocks, so it's accelerating that direction. So I'm going to make the downward direction my positive direction. There's my F equals ma again, and there we go. And that's what I said about kind of treating the downward direction as the positive. And so I've just got to work that out for T, and we end up with 15,810 newtons. Okay, on we go. The force exerted by block P on block Q. So now I need to have a look at what's going on inside my cage. So I've separated that out, and I've put block P and block Q in there. And what I'm going to do now is get rid of those two forces because they're external forces. I don't need to look at those because what I'm going to do is just look at specifically the forces that are acting on block Q. These ones are not acting directly on block Q, so I'm going to get rid of them. There we go, and now I'm just going to think about what's happening on block Q. Right, well, the cage exerts a reaction force on Q, so there's got to be an upwards reaction force from the cage on the block. There's got P exerting a downward force on Q, which comes from kind of necessary part of the weight of P, but it's not just going to be the weight of P because the list's accelerating, so it'll be slightly different. But there's a downward force because P is sitting on top of Q, so it's a downward pressure onto Q. And then we've also got gravity acting on Q as well. So that's all the forces acting on Q. What I'm going to do now is just take the other bits and pieces away, and you can see that's my forces diagram. There's three things that are just acting on Q. Force equals mass times acceleration. Acceleration is going down, so I'm going to treat downwards as my positive direction. So there's my two positive forces. There's a negative force going up, and there we go. And straight away we realise we've got a bit of a problem because we've got two forces there that we don't know about. So that's going to create a bit of an issue. So what I'm going to do now is say, well, okay, well, that's not working out for me at the moment, but my other option is to have a look at what is going on with block P. So let's do that instead and see if that helps out at all. I'm just going to shift that equation out of the way for 1 second and have a look at P. So what's acting on P? Well, we have got Q, which is exerting a force on P, because remember P is sitting on top of Q. So essentially kind of that's the kind of reaction force. And then we've got gravity that's acting on P going downwards, and those are my only two forces. So that makes that calculation a whole lot more straightforward. And straight away we realise that the reaction force of Q on P is 6,510 newtons. Now, the key to this is the fact that if Q is exerting a force on P, which is that size, then Newton's third law says the force that P is exerting on Q is exactly the same, but in the opposite direction. So those two forces are the same. So straight away, if we wanted to know what is the force exerted by block P on block Q, it's that one here in this diagram. It's the same size as that one in our other diagram. And so the answer to our question is 6,510 newtons. And finally, we want part C, which is the force exerted by block Q on the cage. So if we have a little look at Q again, so what we've got is, remember, so we had, here's our block Q. It's sitting on the floor of the cage with P on top of it. So that force there, that's our force that P is exerting on Q. We've got gravity, and the one we're looking for is essentially this reaction force here. This reaction force is the force that the cage is exerting on Q. So therefore, as a result of Newton's third law, that is exactly the same as the force that Q is exerting on the cage. So we need to figure out what R is, and bearing in mind we know our value of P, 6,510, all we've got to do now is plug that into the equation and do a bit of solving, and there you go, there's our reaction force. Now, you might want to spend a bit of time doing a bit of practice on those kind of questions, and then if you've got those all sorted, we can crack on to the next ones, which is the other way in which Newton's third law is going to be examined in the mechanics course, and this one is to do with pulleys. Now, before we start all of this, we've got to put some modelling assumptions in place. So what we've got is strings and cables are often referred to as light and inextensible. Light meaning they've got no weight, and inextensible meaning there's no stretch. The reason for that is because if you've got the mass of the cable to consider, then your tension will change depending on whereabouts within the cable you are, which makes life a lot more complicated. And the same way with inextensible, if your cable stretches, imagine it working like a bit of a string, you'd apply a force, the object wouldn't move, and then the spring would boing, and what would happen is it would accelerate, and then it would kind of get to the limit of its the spring's compression, at which point it would slow down again, and you're into kind of variable acceleration and a whole world of fairly major technical issues. So in order to keep models simple, inextensible, and that's the one that you normally get to comment about in the exam, we'll get a modelling question saying, you explain how you've used a modelling assumption. You're saying, well, I'm going for an inextensible spring, which means acceleration is always going to be constant. The other thing to mention is that any pulleys or blocks or anything that cables are passing over are smooth, which means we haven't got to worry about any loss of energy or anything like that due to friction at those points. Right, so that's all the modelling assumption stuff. Dull but important, because more and more we're seeing questions on the exam where you're being asked to explain how you're using modelling assumptions, so it is important that you're able to talk about those kind of issues. And away we go. So we've got a box of mass 2m. It's placed on the table, strings attached to it, box passes over a smooth peg. For smooth peg, read pulley, same thing. And you've got a ball that's attached to it on the other end, and then the whole thing's released and starts to accelerate. And there's a frictional force acting on the box that's on the table. So again, a whole load of wordy stuff. So we're never going to make any sense of that until we draw a diagram. So here we go. First things first, there's our diagram, which kind of all of a sudden starts to make a whole lot of sense of this great big mass of information. And now we need to have a look at what forces we've got going on within those two objects. So let's have a look at what's going on with the box first of all. So for the box, we've got tension going in that, so that's tension in the string. We've also got a 14 Newton frictional force going there, and for the sake of completeness, I've got my weight and reaction force. So let's have a look at what's our equation of motion, our force equals mass times acceleration, is going to be with regard to that. So it's going to accelerate at 3 meters per second in that direction. So force is mass times acceleration. So we've got in the horizontal direction, t minus 14 equals 6m. And I've just put that note there, so that's mass times acceleration, the mass being 2m, the acceleration being 3, hence the 6m. Right. We needed to calculate the value of m and the tension in the string. Can't do it from here, two variables. So let's now have a look at what's going on with the ball. So let's think about the forces going on with that. So we've got tension in the string. Now, here's the key idea. Because it's a single piece of string, the value for tension there is the same as the value for tension there. So if we can find tension in one of these objects, we can then swap it back into the equation for the other one. The only other force acting on the ball is a force due to gravity, so that's that one. And this thing is accelerating at 3 meters per second downwards, so I'm going to use downwards to be in my positive direction, which then gives me that equation there. Again, two variables, but as we've seen so many times before, two variables, two equations, we can put these things together and do a bit of simultaneous solving. So let's do that. And the nice thing about this, and the way we've set this up, is if we add these equations, I've got a positive t here, I've got a negative t here, so literally just adding these two equations together will get rid of the t's. So let's add them, those disappear, so we've got 5mg plus minus 14 equals 21m. All I've now got to do is rearrange and solve for m. So take the 21m over to that side, move the 14 over to the other side, bit of factorising, bit of dividing, and we end up with the the value for m is 0.5. Right, once we've got our value for m as 0.5, it's a very simple job to go back and say, well, what's going to be our value for t, the tension in the string? So let's put it into there. So the tension is going to be 6 times 0.5, and I've moved the 14 over all in one go. And so tension in the string is 17 newtons. Job's a good one. Right, and so on we go. What we just had was a fairly straightforward question. Now let's go for one that's got a whole world of other issues going on as well. So we've got, in the first example, it was, kind of a particle that was on a horizontal surface and something's dangling over the end. Here we've got two particles connected by a light rope which runs over a smooth wheel. So they're going to look like that. We've got masses of 300 grams and 700 grams. Notice 0.3, 0.7, because we need to be working in kilograms, because Newton, a single Newton is the force required to cause a 1 kilogram acceleration of 1 meters per second. So we've got to work in kilograms to make sure that our units are working okay. And we're told the whole system is held in rest for 5 minutes above the ground, so I've put that in. Let's now chuck in some forces. So on X I've got tension going upwards, I've got weight going downwards, and it's accelerating. It will go upwards when this thing's released. And on the other side we've got tension and weight again. So what I'm going to do is have a look at this and say, well, we need to work out the acceleration of the system. So two equations. This first bit, very straightforward, same principles as what we had from the last slide. So for X, resolving upwards, and again, I like to include little notes here, so I'm making it very, very clear to myself and to the examiner exactly what I'm doing. We've got force equals mass times acceleration, t minus 0.3 g equals 0.3 a. And now let's have a look at what's happening with y. So I'm going to resolve that in the downward direction, the same direction that y is accelerating. So we've got there 0.7 g minus t equals 0.7 a. Right, we want the acceleration of the system, so let's just solve those two things simultaneously. And again, let's just pull the little trick where we're just going to add those things together. So I've got here t plus minus t, they're going to disappear. 0.7 g minus 0.3 g, that's 0.4 g. Add those two things together, we're getting 1a. So therefore a is 0.4 g, which is 3.92 meters per second. Okay, next bit. So we want the speed of y when it hits the ground. Speed, we've got this stuff about kind of held at rest 5 minutes above the ground. Hopefully that's starting to trip a few bells in your head, thinking we're going to need a bit of suvat here. So let's have a look at what we've got when it hits the ground. So we've got displacement, it's 5, held at rest initially, so our initial velocity was 0. V is the thing we're trying to find. We've just got acceleration. T is the one we don't care about, so that's going to be v squared equals u squared plus 2as. Plug all the values in, and we've got v equals 6.26 meters per second. Okay, all reasonably straightforward so far. It's part C where we've got to do a little bit more careful thinking. So let's have a look at what's going on with that one. So we want the maximum height above the ground reached by X. So we've got to think, well, what's going to happen when Y hits the ground? Well, as soon as Y hits the ground, X is going to continue travelling upwards, but Y will stop. And when Y stops, what that's going to mean is that our string is going to go slack, so we no longer have any tension going on. So we're going to have to get rid of that tension force. And once we realise that tension has disappeared, we realise that X, the only thing acting on X now is the gravity. So what that means is we're going to have to completely recalculate our acceleration based on the fact that the force had changed and based on the fact that X is now moving freely under gravity. So here we go. There's my forces diagram. Acceleration going that way, although it's going to be slowing down. And that gives us a result that we kind of already knew. Because let's be honest, let's say if it's moving freely under gravity, then it is accelerating at 9.8 meters per second. Downwards alternative, if it's moving upwards, the deceleration will be 9.8 meters per second. In reality, you don't need to rework this calculation. You should be able to just say, yeah, well, when it's moving freely with no other forces, the acceleration is going to be 9.8. But I just put that little bit there in, for the sake of completeness. Right, so we've now got to figure out the maximum height above the ground reached by X. So maximum height will happen when V is 0. So S, that's the thing we need. U, now, what speed is this thing initially travelling at the point at which everything changes, the point at which the string becomes slack? Well, that's going to be exactly the same as the point, the velocity or the speed that Y was moving at when it hit the ground. So our value for V from previous equation becomes our value for U in this one. V is 0, maximum height reached when X is instantaneously at rest. and we've got A, so we've got that value, and so we need S. So again, we're going to go for v squared equals u squared plus 2as. Plug all the values in, do a bit of rearranging, and solve it for S. So as it turns out, our displacement is 2 meters, i.e. X is going to continue upwards for 2 meters before it stops and starts coming back down. Now, the question of course now is, well, is our answer to the question, is S 2 meters? Well, the answer to that, hopefully you'll realise, is no, because we've got to think very carefully about what's happening. So, they're held at rest 5 meters above the ground before being released, so X is currently 5 meters above the ground. They're then released. Y hits the ground, travelling 5 meters, so that means X has travelled 5 meters upwards, so in total now it's now 10 meters above the ground, and then finally we've got that extra 2 meters of travel, so the total height above the ground is going to be 12 meters. So we've got to be really, really careful in those kind of questions, that we don't just get to the end of the calculation and go, yeah, there you go, where my answer is going to be 2, because a bit of careful thought helps us realise it's absolutely not. The other variation on that one is they might say, well, how far would X travel before the string becomes taut again? In which case it would go up 2 meters, go down 2 meters. At that point, the string would become taut, so the total distance X would travel would be 4 meters. So there's a few ways they can vary that one, but again, it is well worth taking the time to get to your conclusion, come up with an answer, then have a look back at the question and make sure you're absolutely clear on what it is the question is answering. And there we go.